In this video, we're going to look at Chapter 4 of the OpenStax Intro to Statistics book. We're looking at discrete random variables, and we will go through the workbook pages or video companion that you have in your assignment for probability distributions and for mean and expected value. They're synonymous, and standard deviation of a probability distribution. So in Chapter 4, you would have watched the real data videos to get a feel for how this is used. Hopefully you found that helpful. Here's some other examples of discrete random variables. A student takes a 10-question true-false quiz. Because the student had such a busy schedule, he or she could not study and guesses randomly at each answer. What is the probability of the student passing the quiz with at least 70% correct? This example illustrates one type of probability problems involving discrete random variables. We call discrete data are data that are countable. So we're not going to do this problem out right now. It's just kind of the type of problem that we're looking at. So some definitions here and notations. A random variable describes the outcomes of a statistical experiment in words. The values of a random variable can vary with each repetition of an experiment. Random variables are denoted using letters such as X, so a capital X here. Random variable is said to be a discrete random variable if it has either a finite or countable number of values. Random variable notation, we use capital X when we write out what that means in words, and a small x is given as a number. So here's just example 4.1 is just more informational than anything to do. Let X, capital X, equal the number of heads when tossing 3 fair coins. Then the sample space would be notated as the set tail, 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 head, 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 tail, head, 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 tail, head, tail, 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 head, tail, 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 head, 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 head. And we would notate the random variable small x as the number of heads. So we have to define that as meaning the number of heads. So in this tail, 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 that's 0 heads. And then if we want to see where 1 head is, we have head, tail, tail right there. We have tail, head, tail, 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 head. So that would be 1 head. And then 2 heads are the tail, head, 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 tail, head, 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 tail. And then 3 heads would be head, head, head. Probability distribution functions, or PDFs, for a discrete random variable provides the possible values of the random variable x and their corresponding probabilities. So this can come in the form of a table or a graph or sometimes a formula. So these discrete probability distributions, or PDFs, have the probability of x denotes the probability that the random variable x equals, or capital X, what you're talking about in words, equals the numerical value for x. So we have the sum, this is the sigma symbol here, sum of p of x. All those probabilities added together have to equal 1. And all the probabilities are 0 and anything up to 1, so including 1. So 0 less than or equal to the probability less than or equal to 1. So let's look at a couple of charts, for example, in 4.2 here. The one on the left, just ignore the spaces in between here, but we have x. And we don't know what this data is. It's just generic data, but it's just saying 0 occurrences would be 0.16 or 16%. 1 is 0.18, 2 is 0.22, 3 is 0.10, 4, 0.3, and 5, 0.04. So if you go ahead and add all those up, they should add to 1 to be considered as a probability distribution. You also have to look to make sure there's nothing less than 0 or greater than 1. So go ahead and pause the video and add these up and just double check that it adds to 1. And then take a look at the one on the right and you can distinguish if that adds to 1 and if it also meets the other criteria as well. Okay, so I've just pulled up Desmos, so hopefully you've looked at that and calculated that out. And I just took just the probabilities, not including any of the x's, the probabilities of that number of occurrences happening. So I just put those in Desmos and they sum to 1. So that is a probability distribution, because then I also check to see if I have anything less than 0 or greater than 1, and I don't, so I'm good there. And then in the next line, I looked at this column here, put it into Desmos and checked that out. They only add up to 0.95, not 1, so that's one flag against it. And also I have a value less than 0, so that is not a probability distribution. And you can actually, I just copied and pasted the column into here and then added my operations plus or minus. Okay, so the answer for that is yes for A and no for B. In the next example, 4.3, we have the table below shows the probability distribution for a random variable x, where x represents the number of movies streamed on Netflix each month. So we have 0 movies, probability would be 0.06 or 6%. 1 would be 0.58, 2, 0.22, 3, 0.1, 4, 0.03, 5, 0.01. So if you just double check this, and they do add up to 1, all the probabilities, there's no values lower than 0 or higher than 1. So we're good with that. And then we can answer these questions. If I look at what the probability of streaming exactly 3 movies each month is, I would just want to look at this row here, and that would be 10%. So I could say probability of the 0.10, or you could say 10%. Okay, so either would be fine. You would want to check what my Open Math and the electronic homework, what they're looking for. They might specifically say to put it as a decimal or as a percent. So just look for those things, or if they already have the percent there next to the answer box, you have to put it in as 10, and then the percent is already there. So just watch for things like that. The next question is, what is the probability of streaming at least 3 movies each month? So in that case, I would add up the 3, 4, and 5 probabilities. So go ahead and add those together and see what you get. Probability, and you could do the next one at the same time. What is the probability of streaming less than 3 movies each month? So we're looking at not including the 3, just what's under that. So it would be these down here, 0.22, 0.58, and 0.06. So go ahead and pause the video and get your answer for that, and then check back. Okay, so we have probability of streaming at least 3 movies would be 14%. And probability of streaming less than 3 movies is 86%, so quite a bit higher. And you notice that these would add up to 100%, because I'm getting each half. So The notation on that, sometimes you'll see it looking a little differently, so I'm going to write that for you underneath each one, what it would look like more symbolically. Okay, so here's what probability of having greater than or equal to 3 would be at least 3 is 0.14, and probability of x being less than 3 is 0.86. So you can put that in parentheses just like you see here using the inequality symbol. This one for exactly, I would just write it as p x equals 3, like that, equals 0.1. And you'll just see that notation or be using that notation, so I want to make sure you're familiar with it. Next, we're going to look at 4.2 expected value and standard deviation, and we will compute the mean and the standard deviations using GeoGebra. Seems to work really best for this, but Staplet probably can do it too. I'm just not as familiar with that. So what we need to do here is to add up all our products of the number of times something occurred times its probability is just the same as doing a weighted mean, and you can do it out by hand the long way. That's not too complicated, but it's still a little cumbersome. Just as we would have done with a frequency distribution or a weighted mean to find like an average or something. This is the same kind of thing. We also call this expected value later when we're looking at some other examples. If we're talking about like say gaming, like gambling and things like that, or playing cards and doing raffles and things like that, it's called expected value. So you need to have the weight, which is the number of occurrences, times the probability, goes in the far column. And so this one would be 0 times 0.06 is going to just be 0. And then if you do the next one, we would have just 1 times that, 2 times the 0.22, 3 times, and so on and so forth. So go ahead and fill out that far right column to get your product of your random variable, the number value of it, times the probability. So I've filled these in: 0, 0.58, I'm reading down that far right column, 0.44, 0.3, 0.12, 0.05. So if we go ahead and add all those up, I'm just gonna just quick show you in Desmos. You can just go ahead and copy and paste and then put your symbols in, or you can just retype it. But I get 1.49, and that is my mean of this probability distribution. So that just means that it's the weighted average of those probabilities. Now to do this in GeoGebra, you just would want to highlight both columns. We've done this before with other things. Back a few sections ago, a couple sections. So I'm going to just refresh on that. We're going to want to go into GeoGebra Classic. So just always just search that. Go into the Classic. And then you're going to want to click these 3 bars, get to Spreadsheet, and then we would highlight the top row of the 2 columns and then paste And I put my table in. Now remember, this is still one variable statistics. I'm not doing correlation like you did in the last, may have done in a different section. This is just the same as finding a mean of a frequency distribution. So I go here, click my little histogram, hit one variable analysis. I can look at a histogram and see the layout. I could do a bar chart, which is often used for probability distributions, more just skinnier. We actually want to do that because it's discrete, right? So that would be the most appropriate one, is bar chart. And then to get our statistics, we hit that sigma x, and we will get the mean 1.49 right there. We also get the standard deviation. It only shows this under the population one, but that's fine. We have 0.9327 is our standard deviation. So remember that value there for a question we'll do later. So it just hits them both at the same time. Quite nice. Example 4.5, right underneath this one, we just want to write our answers in a sentence. Interpret the mean of the probability distribution in example 4.3. So just think about what that means in words, like over time, in the long term, and what it means. It's an average, and just what you're calculating is number of movies. So we can just say it's, the average, we can expect over the long term would be about 1.49 movies a month. Next, we're going to look at expected value. So we want to find the mean and standard deviation of a probability distribution when we're looking at gain or loss of an event. That's what expected value is. It's obtained by taking the sum of the products of each outcome and the probability of that outcome. And another thing to know is expected value. If it is 0 for the game, it's called a fair game where neither side has an advantage. So we're going to look at example 4.6. In the game of roulette, a player can place a $5 bet on the number 17 and have a 1 out of 38 probability of winning. Just so you know, I want to show you really quickly what a roulette wheel looks like. And it goes up to 36, but it also includes 0 and 00. So that's why there's 38 numbers. So if you're looking at 17, getting 17 here, that would just be one occurrence out of 38 that could possibly happen. So that's how we figure out the probability. And I just looked up American roulette has 38 numbers, including 0 and 00. It depends if you're doing European or French or different kinds of things. You can just double check what they're asking. Usually we try to give that to you within the problem though. So now back to our problem here. If the metal ball lands on 17, the player wins $175. Otherwise, the casino takes the player's $5. So I set up a couple of scenarios in a chart. So I pay $5 to play, right? Or I'm going to win, it was $175. So that's what I'm just stating in my chart to lay out my scenarios. And then I'm going to figure out my probabilities for each of those things happening, and then what the expected value will be. And if I played 1,000 times, how much would I expect to either win or lose? I lead you to believe you'll lose. Usually you do. So Here's a chart with the third column added, where I'm going to do my random variable times the probability. You can just write it out. You don't have to put it in a table, just to help you visualize this. I thought it might be a good idea. So one thing we have to figure out though is, what is this X, right? If we're paying $5 to play, what we win is really -5. Okay, so that is going to happen. We could do this a couple of different ways. We could do that, well, I pay $5 to play and I lose, right? So that would be -5, and that would happen 37 out of 38 times. And then over here I would just multiply those two together. Then my other scenario is I win $175, but I paid $5, whoops, to play. So really what I get is 170. Okay, and that would happen 1 out of 38. So you have to account for that coming off. You could have done it up here. You could make this be -5, and that would have happened all the time, but then our probabilities wouldn't add up to 1. So I like doing this method. It's easier for me to wrap my brain around. And then we go over to Desmos scientific calculator, and you can just type those things in. So you type in -5, then put some parentheses, and that would happen, we had 37 out of 38, and then make sure you arrow over before you put the other parenthesis, and then plus my 170, because I didn't get all 175. I mean, I had to pay 5, so I need my net winnings, and then that would be times 1 out of 38, and then I add those up, and I get -0.3947. So I'm going to make it into dollars and cents, so I can just copy and paste that into my little answer box over here. I really didn't even need to fill those out, but I'll write out the whole thing for you. Okay, so this is the answer written up. You can just out as a string of numbers. You don't have to make a chart. So we can say that after 1,000 games, this person is going to, or we would expect that they would lose $390. Okay, and that's it for this video set. Have a great day.